Hey guys, so it's Mrs. Dr. B. It's way later than I would like it to be, but we're going to go through this. This is going to be my um, everything you need to know about trends of the periodic table for the test. I got to try to get it done in about 20 minutes because it's 7:30 right now. I apologize. It's just not been the day that I wanted it to be, and I apologize for letting you guys down. But all right, so the first slide of this, I'm just going to go through this very quickly. For the test tomorrow, you do need to make sure that you can identify how to do the trend within a period, and simply you're looking left to right. You then need to also be able to say how to do the trend within a group, and that's going to basically just look up and down a single column, and you're looking for whether it increases or decreases or stays the same. All right, so that's the first part of this, and I think you guys are really good at this, so that shouldn't take a whole lot of effort on your part. All right, so we went through this, or at least some of us went through this page as far as atomic radius. What I need to do is spend just a little bit of time to make sure that all of you guys see this. I've rearranged it a little bit, but as you look over here in this drawing, we know that as I go from sodium all the way down to neon, what's happening is we are adding protons. Okay, we're adding protons and we're adding electrons. And so for sodium, excuse me, that's not sodium, that's lithium. Sodium's down here. Lithium. We know that I have 3 protons and 1 valence electron. All right? And we know it's on the second energy level. And what I'm getting ready to do at the same time I'm doing this is this Q1, Q2, where you see this already on the board, because this is this thing called effective nuclear charge. It's a way of being able to describe why. We're not doing this scientifically, we're just doing it as a generalization, that we know that here Q1 is the number of protons, Q2 is the number of valence electrons, and the bottom number D is just simply the energy level that the valence electrons are on. Okay, so when we do this, we see the number. This is supposed to be a multiplication, sorry. 4 times 1 divided by 2, or 3 times 1, I can't look, divided by 2 is 1.5. And what this does is it talks about the charges and the strength of the charges. So if you go back over here to the slide, it says, you know, what do we know about opposite charges? We know that opposite charges attract. And so that's the first thing we need to know to be able to understand this atomic radius. The second thing we need to know about this stuff is what happens. You know, the first question is what happens as we go up and from side to side. The second question is what happens when we go up and down a column. And what we know here is that D value is increasing. All right. So as to answer question 1, we know that the top is changing, right? So we know for beryllium it's 4 and 2. We know the Q for boron is 5 and 3. For carbon is 6 and 4. For nitrogen, 7 and 5. 7 protons, 5 valence electrons. When we get all the way over to oxygen, it's 8 and 6. This is fluorine, which is going to be 9 and 7. And when you get down here to neon, it's 10 and 8. So that's talking about the first part of what we're looking at over here on the slide. And we understand that they attract each other. And so what we're going to be doing with this equation, it's kind of end up halfway through it, is that we're going to take those two things and we're going to multiply them. But the other part of the equation is the energy level of the valence electrons. And so what I need us to do is consider the fact that the valence electrons, based on the circle that you're seeing here, you can see are getting farther and farther away from the nucleus, because the nucleus is right there. These valence electrons are relatively close. They're at the level 2. These are going to be down at level 3, and these are going to be down at level 4. So all the way across this period, all of these have a 3 on the bottom on the numerator or denominator. Whereas everybody on this row has 2 on the bottom because the valence electrons are on the same energy level. Right? So what this math problem does is it estimates, it's just a good quick little way of being able to say how strong is the attraction. Right? 2 things, so what we're kind of doing is they're saying 2 things that affect how much attraction exists. One of them has to do with the number of charges. Just like magnets, we know the stronger a magnet, the stronger attraction, more charges, which is the numerator. The numerator is the number of charges. And the other thing that we know about magnets is the closer they are, the more they work. So the attraction is going to be bigger when you're in a lower energy level. These 2 things together basically explain why. Number 1, the hydrogen is smaller than lithium. Why? Because we've added an energy level. Lithium is smaller than sodium. Sodium is larger than potassium. But more so, they explain why lithium is larger than fluorine. And it doesn't have to do with, there's more of, it has to do with the fact that there's more of them, but more of them actually makes the attraction stronger. So when you come down here, it says more charges, makes stronger attractions. It'll bring the electrons in closer to the nucleus. All right. So the only other thing I really want to do with this is make sure you can see the trend. I told you, for those of you who didn't bring this at home, you would see these graphs. Here is your atomic radius graph. If you see it on the slide as well. And what you just need to understand is this would be, for example, level 1, level 2. This would be lithium. And this end of it, this would be the fluorine, neon end of it. And what we're looking at is a number of protons of 3 and 1 valence electron. Versus fluorine, we have 9 protons, and we have 1, 2, 3, 4, 5, 6, 7 valence electrons. If we're coming down here, we're now on sodium because it's 1, 2, 3. We're going to have now 11 protons. All we're really interested in is the valence electron, so it has 11 and 1, but we are now on the 3rd energy level. So hopefully that makes sense to you. Okay, we also talked about atomic radius and ionic radius. The only thing I really need you to be able to do for this, and I don't even think I left it on the list, is that the cation is smaller than the neutral atom. Here's your neutral atom. Your cation is positive. Why? Because it lost electrons. It did not, however, lose protons. So if we're still talking about lithium, we knew there's 3 protons working on 1 electron, and here we still have 3 protons and there are no electrons. So those 3 protons can pull everything else in a lot closer. So cations are always smaller than the neutral atoms. On the other case, your neutral atom here, if this is going to be, let's say, oxygen, oxygen has, 8 protons, 1, 2, 3, 4, 5, 6 valence electrons. It's in group 16. When you add, and we're going to do 2, we're going to make this oxygen 2 minus. That means we added 2. We still only have 8 protons working here, but now those 8 protons are being shared and trying to hold on to 8 electrons. It's harder for 8 protons to hold on to 8 electrons than it is for us 8 protons to hold on to 6 electrons. Okay, next up, very quickly, you got to be able to read these graphs. We've talked about this again. You need to remember that each of the spaces is the end of the row moving back, end of row, each row, whereas the very last element, the very last one in every one of these guys are the noble gases. All right, so there's your noble gases with every one of these. The very last one. The very first line on every one of these is going to be group 1, which we refer to as the alkali metals. You do not have to remember that, but we're going to call those, I'm going to do the @ sign just because I needed someplace to do it. So there's an @ sign. That's hydrogen, there's lithium, there's sodium, there's potassium, there's rubidium, right? So a period is from group 1 to the noble gases. So this is a period. This happens to be period number 2. This is period number 3. Period number 4. Period number 5. We got period number 1 right there. All right. Make sure you can read the graph. Make sure you remember that trends across the period are going to be looking at this entire section, whereas trends within a group or down a group is going to be looking at, say, for example, only column 1. All right. The only 2 models you will see, where did it go? I don't think I printed this one. All right, we're not going to, I can't do anything about it. If I didn't print it, I didn't print it. We're just going to have to talk about it over on the thing because I'm not going to stop here. All right, compare the models even though you see these things that are different. Again, the whole idea is I might just have to come back with another view of what we were just looking at. Don't know why I didn't print number 6. I thought I did. Huh. All right. Well, let me find one that's a little bit easier than I know. I thought I did it. Hang on. Let me pause this. All right. So what I've got to do is I just made a copy of that last slide. Hopefully I can get it back over here. So the idea is what I want you to be able to do, and this is where first and second period you're going to need this. Those of you who were in 4th, 5th, and 6th, 7th and period, you've already seen this. But to compare the 2 models, this is what you guys have created. This is a model that would be given to you that shows the things using Excel. Again, there's your end of your rows. It's pretty easy to see this. This is a whole lot easier because you know exactly when you start back over. So to look at the top drawing across the period, if you'll please watch the slide, you'll be able to see. This is why I didn't bother making a copy of it because you really didn't need it. Because you're going to watch it happen. All right, any single row, okay? When you're comparing models, you can see similarities by looking at, or you can look at the trends by looking across any single row. If you are looking at the bottom drawing, you're going to just basically take any section. All right, that's the same trend. You can see in both cases that atomic radius decreases. All right, now let's talk about trends down a group. On the top drawing, all you have to do is look at any particular group. Normally, most people go to group 1 or 18 simply because they're the easiest ones to see and have oftentimes the largest amount of variation. If you are looking at the graph at the bottom, however, what you're going to do is you're going to find a single element. You're going to find, for example, either the first data line or the last data line. I chose the first one in this particular case. You can see that I just took the first element in every one of them. I highlighted it with a star. You don't have to highlight it, you just need to be able to see it. And then you can see I drew a really bad line going from one part to the next. So you need to be able to look at both of these. I'm not going to tell you, I'm not going to ask you to compare them, but you might have to use one or the other for your test tomorrow. Do you see the trend? One trend might be on the top picture, another trend, a different property might be on the bottom picture. So I'm just trying to ask you to make sure you know how to compare them. All right, so now we're going to get into the part that nobody's done. And this part is the idea of what these things are. Ionization energy. Guys, you got to know the definition. It is the energy required to completely remove an electron from a gaseous atom or ion. How much energy does it take to pull it away? All right, so here you see this picture, and I'm going to draw it over here so that we can go as fast as we possibly can. We already know from atomic radius, larger atoms hold electrons less tightly. Why? Because of the distance. Distance from the nucleus. So guys, this is why atomic radius explains every single trend. Okay? Since larger atoms hold electrons less tightly, the amount of energy to remove electrons is going to be lower. Larger atoms equal lower ionization energy because it is easy to pull a valence electron away. On the other side of it, smaller atoms have larger ionization energies. And guys, here's what your trend says. Let's look. We got a small atom here. Let's go with the atomic radius. You got a small atom here, and it has a very large, comparative to the other ones in the column, a very large ionization energy. All right, if we go across the periodic table, he's large, he's going to get smaller. Let me do it this way, and then we're going to get smaller and smaller and smaller and smaller and smaller. Why is that ionization energy getting? Oh, because it's getting bigger and smaller. Okay. Smaller atoms have a larger ionization energy. Larger atoms have a smaller one. Why? Because it's easier to pull electrons away from something that is far away from the nucleus. All right. So here's this graph, and you can see that it decreases. Where it decreases going this direction. It decreases going down. It increases going across. All right, let's look here and see. Again, here's your period, and look, it increases going across. All right, now these other ones have to do with first, second, and third ionization energies. We're not really going to worry about that right now, but let's just take, instead of the first one, let's put a star here on the last one. There's the last one. There's the last one. This is called third ionization energy. You don't have to know what that means. But look, guys, you can see the trend is down. You see a smaller and smaller ionization energy as you go down. So the biggest thing I need you to be able to do here is understand why is this important. Why this is important is because if you understand that the large atoms are on the left side of the periodic table, then we should be able to understand why the left side of the periodic table, these guys are negative or positive ions. They're cations. Why? Because they lose electrons. It is easy for them to lose electrons. The guys on this side of the periodic table are anions. Why? Because they can't lose electrons. they have too large of an ionization energy. So large IE means atoms don't lose electrons. Okay? And that's on the left side of the periodic table or at the top. Down at the right side and at the bottom, we talk about small IEs, mean that they lose electrons easily. Okay? Make sure you can just read the graphs and understand them. That's going to be the most important thing. We're not going to spend a lot of time on the rest of it. I do need you to know the terms, though. Okay? All right. Electron affinity, you're not going to be doing the graph, but you do need to understand what it is. All right? You're not doing the graph, not on your test. Not on test. All right. Electron affinity is the opposite of ionization energy. All right? It is the energy change that occurs when an electron is added. When it is added. All right? So the idea is if you've got this guy over here and he's got all of these electrons, he's small because there's a lot of electrons there. There are electrons floating all around all of these guys. Right? The protons are trying to hold on. Protons can't hold on to these guys. This is too big. If it is too big to be able to hold on to its electrons, it's not going to be big enough to be able to gather any. These guys, however, are holding on to electrons tightly. If they're holding on to electrons tightly, there's going to be room for them to come and get this guy and lasso him and put him right back there. So the take-home message for electron affinity is this. Atoms with a high electron affinity become anions because they gain electrons easily. Let's go back over here and I'm just going to show you this. This is exactly what we just said. The guys on this side, because they have a small ionization, they lose. The guys on this side have a large ionization energy, so they cannot lose electrons. If you can't lose electrons, then what you're going to find out is, like these guys over on this side, they have a high electron affinity. The word affinity means love of. Okay? You look at the pictures over here to the side, it says, I love electrons. Or you go here, this guy who's got the high electron affinity, look how crazy he's going with the electrons that are floating by. Random elements are going, okay, well, whatever. And you look at your noble gases, and they don't care. They don't need an electron. Who cares? All right. The last one then is electronegativity. I'm at 23 minutes. I wanted to be less than 20. I'm sorry. Again, those of you who don't need all of it, you can move away from this as you need to. Electronegativity is, it's related to electron affinity, but guys, this is the one that I get so irritated with by the end of the year. Electronegativity is probably the trend, the property that we use more than anything else. Electronegativity is an atomic property that describes, if you look at the picture up here in the upper right, these two guys are wanting to share electrons. They want to create themselves a covalent compound that shares. But the guy on the right has a high electron affinity. What does that mean? It means he's got a small radius. This guy has, if you look at the picture that I'm doing over here on the left, high electronegativity. This guy, because he is big, has a low electronegativity. Look at your drawing here. The guy from the left, which is big, has a low electronegativity. The guys on the right have a very high electronegativity. These guys have even electronegativities. All right, so the drawing goes like this. If you look at what's here, is this guy is sharing and he's reaching out to just where he is. This guy, on the other hand, with the high electronegativity, is not just reaching out, but he's reaching farther and pulling it in. These two guys are sharing evenly. They're not, one's not pulling harder than the other. They're sharing evenly. So small elements, again, look at the size here. I'm just going to make this kind of weird. There, we're getting smaller. Okay? The smaller you get, the more you're going to pull on electrons on somebody else. The definition is not to pull in electrons from outside. It does not say that. It says it's the atomic property that describes the tendency of an atom's ability to attract shared electrons. Not loose electrons. Loose electrons is electronegativity. Okay? Loose electrons, when it adds electrons to a gaseous element, it's not ones that are there, it's one that pulls in from outer space. Electronegativity, guys, is when they shared electrons and they pull on them harder than the other guy. All right, and there's the graphs. You can see the graphs the same way. You can see in both of these, as you go from left to right, electronegativity is increasing. You can see it happening here too. When you go top to bottom, you can see electronegativity. It works better sometimes here in the middle, is decreasing. One is always increasing, the other one is always decreasing. So if we're going to look here at the end guy, there's 1, 2, 3, 4, and you can see electronegativity as you're getting farther away from the nucleus, because you're now looking on period 1, period 2, period 3, period 4. This electron out here, this guy out here has 4 energy levels. 4 energy levels. So 4 energy levels makes it farther away. If it's farther away, it's the last level is farther away, it's not going to be able to pull as tightly. Okay. Very last slide is this, and this is just effective nuclear charge. Obviously, this is way too much for you to have to do tomorrow, but I just want you to see it. Okay, effective nuclear charge is just the reason. It is at Q1, Q2 over D. It's the reason why all of these trends occur. All right, 28 minutes longer than I wanted it to be. Pick and choose what you need to see, and I will see you over in the online study session in about 2 minutes. All right, thanks, guys.